Okay, so I am going to talk about enthalpy changes now, because before I talked about internal energy change. You want to finish off the three introduced terms. Now you start to, these equations make sense to you, and then start to get familiar. One of the practice that was given in the textbook was, what about alpha, which is temperature change volume? So that's a thermal expansion, and using D as an nRT over P, that's an ideal gas. You can see that thermal expansion constant is actually 1 over temperature. And this is pressure compressibility, isothermal compressibility, and if you use the same equation, you'll find that 1 over pressure is compressibility. So this is some of the example. What I'm going to, now this section that I'm going to talk about is pressure change, temperature change. I want to know about the enthalpy change. And this one is now they introduce this experiment. Joule-Thomson experiment, Joule-Thomson constant. And this is, whatever the experiment with a name after somebody, he has a very kind of innovative idea. And this one, it is too. And this is, I hope I can kind of cover this Joule-Thomson experiment, a constant process. And this one is, can you see this? Ice enthalpy process. Do you know what's keeping constant? Isothermal is temperature constant, right? Isobaric is pressure is constant, right? Ice enthalpy, do you know what's constant?
Enthalpy?
That's right. So enthalpy is constant, and they kind of designed the experiment there where enthalpy is constant, and this is a process. I think that probably I need to spend extra time in the next class to give out this to you. But let's get started at something that is as simple as what we've been doing. So you guys can do the same thing as I do. dH. So my choice is pressure and the temperature change, right? So what do you write? Pressure change. Temperature change, right? So this is how I'm kind of unravel the quantity of that I'm interested in into two terms. Yeah, and then we just write. Okay, so that's a pressure change, enthalpy change, keeping the temperature constant. That's the same thing. So if I'm going to change the temperature goes down here, enthalpy goes up, and keeping the pressure constant. And now you start to see the choice that I make. Let's deal with something that is easy to deal with. This is, what do you call this? Heat capacity under constant pressure. Right? But now this is something that is not easy to deal with. We're going to deal with this. So enthalpy change when you change the pressure, keeping the temperature constant. This is something that I don't know how I can deal with this. It's not like internal pressure idea. This is something different. So it's coming from this. You have to understand this. Enthalpy, pressure, T are interdependent. They depend on each other, right? So once you define pressure, temperature, H is defined. In other words, enthalpy, pressure is defined, your temperature is defined. So this is the same thing as somebody is saying this. If you have an x, y, z, they are all independent functions. In this case, you will have this mathematical form round x, round y, keeping z constant. So this is the first derivative. Multiply. So now using this, this one goes up, that goes down, and this one is kind of circle around. X, Y, Z, they kind of circle around in this. So once you write it, it's naturally for me to write Y, Z, keeping X constant. Can you do that? Right? So what's the last one? This one goes up, that goes in the bottom. So it's round Z, round X, keeping Y constant. So this is a cycle relationship, and this one is mathematically defined as -1. This is in your creep sheet that was also given to you. So this has nothing to do with the physical chemistry. This is just a math. When they are interdependent each other, this is what it is. So now we have an opportunity to just rewrite that equation into this form. So let's just do that. Okay, so change in H, change in P. I'm just saying they are all related to each other. So once you write this, I can write both pressure change and pressure change, keeping H constant. Okay? And then what else? Temperature change, H change, keeping pressure constant. That is -1. I'm just writing this same equation. Nothing so far is okay. Now let's have a look at that. Can you see what's this? This looks familiar to you? That's right? Enthalpy change, temperature change, keeping the pressure constant. So this is gotta be related to CP, right? I mean, I will come up with exactly actually 1 over CP, but it can be easily taken care of. These are the two terms. And the one term, which is this, do you see that? Yeah, it's right there. That's what I can do, right? So I'm just left with this. This is seemingly more challenging than the other one, but the answer is actually this is more easier to deal with. This is where your Joule-Thomson experiment comes in. Okay? Joule-Thomson experiment keeping your H constant, pressure change, and the temperature change. And I'll have a actually different version of doing this. But this is what this so far is. So okay, so starting from here, and I think that you guys know, if you have a round y over round x over z, you can write round x, round y over z. You can flip that. You guys can, you can do that. You're allowed to do that. So here, what I'm going to do is, because this is a term that I'm interested in, I'm going to flip this equation, or flip these expressions, and put the minus sign on the other side. So let me do that. So, okay, so this is something that I want to know. I have to figure it out. And that is essentially minus, and I'm going to just flip this one, okay? I'm going to flip this, 1 over temperature, 1 over pressure, keeping the H constant, and this one is round H, round keeping the pressure constant. So, wow, so that's what I'm getting it now. And this one, I'm keeping the minus sign here. This one is defined as Joule-Thomson. They use a J. Mu, this is a mu, and this is a CP. Okay? So this is what is called a Joule-Thomson. Okay? I'm going to have a separate section about what this mu means, but just for me, this is something that is involved constant enthalpy, and you are actually recording your temperature, then you change your pressure. Okay, I'm going to get back to you on this, but that's what Joule-Thomson is doing. They compress the gas and they release it, and they measure the temperature change. This is something that is naturally we want to do, and this has a very practical actual meaning here. And then this one happened to be what we call the mu. So once again, this constant mu is, I want to know my temperature change when I change my pressure, keeping your enthalpy constant. And that's a new variable that I am come up with. So then, having come a long way, remember this one now is minus mu Cp dP Cp T. Compare that du is pi T dV Cp dt. So now I have what I have done so far is dH, or changing the internal energy. Those are some sort of the energy. Okay? You can think about, this is not correct to say it's an enthalpy is an internal energy, but internal energy plus PV, which is sort of the system's energy under constant pressure. The pressure can be varied, and that's enthalpy. And that energy state that we actually typically measure, because heat transaction under constant pressure, can be expressed with something that looks like we can measure, or somebody dared to put a name on it, right? Joule-Thomson constant Cp. What was it? That this is an internal pressure and the Cv. So we can start to unravel this quantity of an interest into something that we are familiar with to change. So that's a practice that I want you to have it in mind, and then this is what's the actual main purpose of this class shown up here. Okay. Okay, so this is the one. And then I have a kind of speaking this around. That's a 3. This is 2. That's the number 3. We'll just put a number in there. Okay. The last one that I wanted to show you is, do you guys remember I derived this equation, the heat capacity, because we talked about Cp and the Cv for this. The relative difference is minus Nr, or Cv Cpm and Cvm is on R. That's for the ideal gas. Remember this? This is but what about the real system, or the more generic system, which is defined by thermal expansion constant or compressibilities? These are all has something to do with the real property of the gas. And then I have an expression that if you want to really has to deal with. And then just so this is for ideal gas. 4, 2 for real gas. Cp minus Cv. Isothermal compressibility. Thermal expansion constant. So this is an equation that was derived to the 11 text. Okay. This equation can be derived as well, just more elaborate. I don't think that is, I just show you that to emphasize the meaning. What seems to be seemingly Nr for real ideal gas. A real gas can be expressed by this, something that we can measure, right? And they can be expressed in this. I'm not asking you to derive this, but trying to have a meaning of, when you see different equation, trying to understand why they're expressing this one in this way. Okay. So now time has come to talk about the Joule-Thomson experiment, or Joule-Thomson effect. Actually, let me just probably put this one up to that. and to see if this will make sense. Probably I will kind of show it to you later why this is an isentropy. That's the probably next class. But let me just show you what most people would like to do. This is what most people want to do. So I have a gas in this one, and I want to compress it. Okay, I compress it, and I have a nozzle. I open it up, I let them expand. And you want to put the thermometer that is the temperature is going to go up or go down. That's an experiment that people would like to do. So it's a, if I have a, people can use a compress and then let it go and things like expand, right? So the nice demonstration is actually this. I got this idea from the Joule-Thomson experiment having these syringes. Let's think about the most easier way to define it is this is a compressed gas, right? High pressure, small volume, and then this is lower pressure, expanded volume. So we have to just do this way, and I'm going to draw this one more time next class, so don't worry about it. But concept is important for you guys, okay? So this is a high pressure, smaller volume, and this is some sort of the porous plug, and then there's a piston that is just sitting there. This is your system before, and then next system is you have a piston that has a much bigger volume, and then you kind of use it up. And this is a P2V2. And this is sort of the expansion process. So what you do is now is you compress the gas, you release to the surrounding, and you compress the gas a lot, and you have a nozzle, and let it expand, and to see how much of the temperature change. So what you do in this experiment is, I'm interested in, I want to know what's my temperature change. As to your interest, at the expenses of compress the gas and the release. Right? So what you are manipulating it? You're manipulating. You want to know